Okay, indeed. Good morning, all, and welcome to the last day. Probably is a good morning. And today, what I will try to attempt again, is the following. Given very brief, but hopefully somewhat functional introduction to random matrix theory. But really functional in the sense that we're not going to go into the really nice and deep mathematics of this. Well, there's so much of literature, and of course time is limited. And I will also concentrate on eigenfunctions, because that's what kind of also feeds back into the second part, which would be entanglement and quantum chaos. And thermalization, I just mentioned towards the end, hopefully when I come to that. So I have a bit of I made some slides so that I'm a little bit more organized. So it's thermalization and just a glimpse, very barely, a glimpse of the so-called eigenstate thermalization hypothesis, which has as its input random matrix theories, quantum chaos, at least as it's still an hypothesis, it's not proved as a theorem, but behind it, it has these kind of scenarios, and if a system is non-integrable, it will thermalize rapidly and will follow this hypothesis is the belief, current belief. So it's an ongoing story. But as far as random matrix theory is concerned, it really started in 1930s with Wishart. I'll come back to this name. But from pure statistics point of view, he studied correlation matrices. So that was 1930s really. And then Wigner, 1950s, who apparently was aware of Wishart's earlier work. And Wigner's motivation was understanding resonances in heavy nuclei. So there was a situation like in hydrogen atom where you have the spectrum, but you didn't know what they meant. But in this case, you had a very large amount of spectral data, and it was difficult, impossible to assign quantum numbers to these. And so Wigner decided that perhaps a statistical approach to this spectra would be useful. So this entire field of statistical spectroscopy really started. And here shown in this first figure is actually from a review of modern physics, 1983, by Brody, French, Pandey. So it's a very active group that actually furthered this thing. So at that point, there was a fair amount of data from heavy nuclei resonances, and they constructed something called a nuclear data ensemble from many different nuclei. What they did was they had these resonances. They found so you could just think of them as some energy eigenvalues, if you would, like what we were discussing yesterday, and looked at spacings between them. So the nearest neighbor spacings, or the gap distribution in these spectra, normalized so that the average gap is 1. So that's the unfolding that I was talking about yesterday. If you do an unfolding, then naturally it will fall into a spacing equals 1. Once you do that, and then you plot this, so there's experimental nuclei data that followed this kind of a curve, and then this is a famous a curve that I'll be talking about, called the Wigner surmise for this quantity spacing S, a distribution S, which is pi by 2 S e to the minus pi by 4 S squared. So basically a distribution that vanishes S equals 0 as a Gaussian tail, and it's normalized so that not only is the average integral of PFS is 1, but the average of spacing is also 1. That's what all these pi by 4s and pi by 2s are. So this is a Wigner surmise, which we will talk about, but it fits pretty decently this nuclear data. So what it shows is actually that no two resonances are close by. The probability of finding nearby resonances is very small. And this is some other thing, but actually we won't have time to go into that. So some other statistics of that. But that also fit this so-called, this curve here, the nuclear data fit. And here also there is this 3 letters here, GOE, which refers to the Gaussian orthogonal ensemble of random matrices, an important ensemble, which I will discuss in a minute what it is. But it's a statistical ensemble. That's what an ensemble is. It's a collection of different realizations. And so this is the predictions of this random matrix ensemble. So this has nothing to do with nuclear physics per se. They've thrown out there's no information about the system except symmetries. Symmetries like time reversal, parity have to be taken into account. Modulo those symmetries, and they're very important, there's no other information about the exact form of the Hamiltonian, which is anyway not well known. So the understanding was that these systems are so complicated, many body interacting systems, that the Hamiltonian itself looks like some kind of a random matrix. And what kind of a spacing distributions or gap distributions can be expected from a random matrix? This is what Wigner surmised, and so and it fit with nuclear data. So it was a happy situation. And this theory was developed in the 50s and 60s by very intensively by Freeman Dyson, Madan Lal Mehta, Gaussian. Principally, Mehta wrote a book which is still a classic on random matrix theory. I don't know exactly when he wrote it, but it contains all the classic information. But okay, yes, so let me go on. So here is a picture which I've taken from also a nice article. Actually, I have done very poorly by way of references, but there was a Lesouche, 1989, called Chaos and Quantum Physics. Beautiful set of lectures by several people. This particular picture is from an article by Oriol Bohigas on this. And what you see here is just a comparison of different kind of numbers. Okay, so the first one here is called Poisson because it's coming from some random process, independent. Imagine that you are generating independent random variables from some distribution, uniform, normal. Let's say some distribution. Let's say uniform to fix our minds, right? And then you take the you arrange them in an increasing order, and then you ask, what is the spacing between them? And you make the spacing, average spacing to be 1. So there is no correlation between, the only correlation is that this is larger than this. Otherwise, it's a random process of arrival there. Then it's not hard to see that such a process is having a spacing distribution which is exponential, e to the minus s. There is a lot of probability for 2 levels or 2 of these numbers to come very close to each other. They are not correlated. They are not correlated enough to avoid each other. Okay, so that's a very different distribution from that of Wigner's, because Wigner says that it vanishes at s. This one is maximum when s equal to 0. This vanishes at s equal to 0. So this is how a set of Poisson levels would look, or numbers would look. These are how prime numbers look. Okay, so completely different. You just arrange all your prime numbers, and this is how the this heavy nuclei resonance looks, the energy levels of that. This is the Sinai billiard. I told you what the Sinai billiard is, a square in which you remove the circle inside a completely non-integrable system. That's the Sinai billiard eigenvalues. These are the zeros of the Riemann function, which I also mentioned on the critical, on the line. Real part equals 1/2. And this is the harmonic oscillator, uniform. Now, I wish there was also an integrable system thing here, like a circle billiard, but this one you can think, well, this is certainly not like an integrable system. So in fact, this one here is like an integrable system. Like if you did for a circle billiard, you would get a Poisson distribution. And what you see by these small things here is that two levels have come very close to each other. Let's say that the mean spacing is 1, it's much less than 1. So these two things have come very close to each other. In the case of prime numbers, they are like twin primes, right? Twin primes are the closest to each other. So these are the occurrences of twin primes. And what you see is that in the case of a Poisson spectrum, the probability of finding two levels close by is much more. That's what this indicates. E to the minus s, s equals 0 is much larger. Prime numbers almost looks like that. And then this spectrum is much less. There is only 2 of these. Whereas here there are so many more. So this is much less. Coming together of that, that is this S here, indicating that. And what about the Riemann zeta zeros? The Riemann zeta zeros have nothing coming together. They are really avoiding each other. And this is another remarkable distribution which follows Gaussian unitary ensemble. And they write the exact numbers, but it goes as some constant s squared, some other constant s squared. So this is the OE, and this is the orthogonal ensemble. This is the unitary ensemble. The unitary ensemble has even more level repulsion. S equal to 0 is even less possible to find in the sense that it's now even finding small things even smaller than for this thing. A rare event, very rare event to find levels very close. Sorry. So, yeah. Yeah. Yes, so there is some thing with the circle. I think with rectangle, you see the rectangle eigenvalues are absolutely simple to write. Alpha is irrational. That's a rectangular thing. Yes, so there is some. Yes, but I mean, I think it's still not like a very complete thing. I don't know whether, David, you know, there is. Yeah, there is certainly some amount of evidence towards that, but I wouldn't say that it's proven to be that. So, but let me also say that for all integrable systems, which means that this is like one of them, so this work really goes back to Berry and Tabor in 1979, where they show that for integrable systems, this is true under some semi-classical assumptions. So in the semi-classical limit, this is true. So the only integrable system which is not valid, and there are always exceptions, is a harmonic oscillator, in which it's flat. And then you have only nearest neighbor. I mean, you have this. And then, I mean, even coupled, not coupled, but separable, this kind of spectrum, it's a very interesting, but it's not generic spectrum. It's because of, again, the action surfaces are flat. No, it's not Poisson for this. There's some interesting math behind that. There are very few exceptions, but one understands those exceptions. But otherwise, it's this. In fact, it's an interesting exercise and a simple exercise to generate these numbers. And it's actually very curious. When I first came across this, I was very puzzled why integrable systems' eigenvalues behaved as if they were a random process, uncorrelated eigenvalues. It's because of this fact that you have these independent quantum numbers. There are no quantum numbers in the case of a non-integrable system. The only energy is conserved, and then there are all these correlations between these eigenvalues, which is not there in this case. So, okay, nucleus is too complicated. It was realized in 1980. Actually, there are some precursors, but it was realized in 1984 in this paper. It was made very clear that there is a connection between random matrix theory, and actually very simple systems like what we have been discussing, like particle in a cavity or a billiard system. So this is from later data from Arndt Barker, but this is for this cardioid billiard. So for the cardioid billiard, you find energy eigenvalues, you unfold them, as I said. In the case of billiards, it's not hard. Average spacing is 1. And you see it follows exactly the GOE universality curve, the Wigner surmise, just as the nuclear data did. So it follows it pretty well. And this is the Poisson which you expect for an integrable system. If you go to the circle billiard, which is integrable, you see that indeed it follows the exponential to a very good extent. So, so such evidence tells us that if we have a non-integrable system, completely non-integrable system, that means that no islands of regularity, significant islands of regularity, you would expect this nearest neighbor spacing distribution to be the Wigner distribution or the Poisson, the GOE distribution. And if it was integrable, it would be the Poisson. But just as a practical warning, you have to do this analysis in a given symmetry sector. Should not mix symmetries, because if you mix symmetries, that means that there is no correlation between these levels. And you will get Poisson, although it's actually probably a GOE or something which looks like Poisson. Okay, so this is actually from the original article of Bohigas, Giannoni, and Schmidt, where they took the Sinai billiard. See, this is where the desymmetrization comes. So this is only 1/8 of the Sinai billiard. You'll have to reflect it different times. So put appropriate boundary conditions, and they found that the Sinai billiard eigenvalues had the fluctuations of the GOE. Okay. Yeah, so you need to block diagonalize, reduce it. Yeah. All right. So I'm going to give a brief discussion. There's going to be a brief discussion of where this surmise is coming from, and as everybody does, and actually as Wigner started out, we're going to just do 2x2 matrices and generalize them. We're just going to state the general results. Any practical clarification at this point? Okay, so this part of the notes I have not yet uploaded, but I'll send it up. So it's the third part of the thing. So what we want to construct are matrices which have elements that are random in them. So we're familiar with random numbers. So we would like to put them in matrices and then ask what is the corresponding distributions of eigenvalues, eigenvectors. So the simplest matrix that we can take is a 2x2 matrix. So let's take a 2x2 matrix. Let's call it X, Y, Z1, Z2. Okay, that's a matrix M. If we take just one number, let's just take one of these variables, X, and it's distributed, let's say, in a normal way, normal distribution with 0 mean, maybe with some variance, sigma squared. Okay? So we know how that looks. Some sigma squared. Variance is there, is zero centered. So that's how if you take a single number, there's nothing to it, you can think of it as an eigenvalue itself and is distributed. Now the question is, if we have a 2x2 matrix such as this, and we have random entries which are independent, so these are all independent random entries, then M itself is an example of a random matrix. And if we take them to be, they can come from any distribution, but let's fix our mind. Let's say that they come from this normal distribution. It's a Gaussian random matrix. And such an ensemble is called a Genebre ensemble. Strangely enough, one of the most, studied much later, not very strangely, but I'll tell you in a minute, so 1964. The fact that this was studied later than the orthogonal, the GOE, and so on is simply because it has no structure. Its eigenvalues can be anything. To again fix our minds, let's say that these fix our ideas, let's say that these are all real. Okay? Then, even though they are all real, the eigenvalues are not guaranteed to be real, as we know. And since we are interested in quantum spectra, we would like to restrict ourselves to Hermitian operators. And if they are real entries, it's symmetric operators. Okay, so let's restrict ourselves further to when the Z1 equals Z2 and equal to Z. Okay, so that's the simplest symmetric random matrix that we can construct with independent random variables putting in. So you could just take your computer, generate 4 random numbers, independent, you have one random matrix realization. Do it 1 million times, you have a random matrix ensemble. It's as simple as that. Now, if we diagonalize this, we would get some eigenvalues. Now they are guaranteed to be real. So you have lambda 1, you have lambda 2, and you also have an eigenvectors. Now, this being a symmetric matrix, it is diagonalized by an orthogonal transformation. M is an orthogonal transformation, this diagonal matrix with these entries, right? So, and an orthogonal 2 by 2 matrix is simply characterized by one angle. Let's say that we take that to be O. Right? So, as far as the eigenvectors are concerned, there is only one piece of information that is needed, this theta. You can construct both the eigenvectors out of that. It's normalized eigenvectors. And that also fits with the number of variables. You see, there are only 3 independent variables here in this matrix, x, y, and z. And in this also there are 3 independent variables, these 2 eigenvalues and this angle theta. Okay? So now, if we select these to be random variables, the question is, what is the distribution of these angles and this angle? What is the distribution of these eigenvalues and this angle? What is the joint probability distribution of these eigenvalues and this angle? That is the question of random matrix theory should first answer. And it's generally a hard question, except for a certain class of ensembles. And I give more, I think I should reset this time. I'm sorry about that. But so I kind of give a motivation in the notes, but I'll skip to the I'll kind of skip to the definition of the ensemble here and indicate why that makes sense to consider. Okay, so we consider this is the definition of a Gaussian orthogonal ensemble, 2 by 2. Gaussian orthogonal ensemble is this matrix M as I wrote it, but these x, y, z are indeed independent, normally distributed numbers. However, they have this relation in their variance. The variance of the diagonal elements is sigma squared. The off-diagonal element variance is 1/2. Okay, so you can generalize this to an n by n matrix where all of the diagonal elements have some variance sigma squared and the off-diagonal elements have half of that. The variance is half of that. That is the definition of the Gaussian orthogonal ensemble. Again, it's a bit confusing terminology. The orthogonal ensemble does not consist of orthogonal matrices. It consists of real symmetric matrices. Okay? Real symmetric matrices. So the fact that this orthogonal comes in a minute. So let's just see the joint probability distribution of these matrix M. What is the probability of finding this matrix M? M is just described by these three numbers. So the joint probability distribution of finding this is probability of finding the matrix M, or rather the probability distribution of finding M. And that's because they are independent, it's just the product of these. And this is where you see the design of dividing by 2, because now there is no 1 over 2 there in this. There's just 1 over sigma squared because the 2 cancels with this thing. So that's just the general. And we can take out 1 over 2 sigma squared common, and this is the construct. But that, you see, is nothing but trace of m squared. Okay? So if this had also been sigma squared, we could not have written it as trace of m squared. And this is true complete generality. An n by n matrix is described by this. So why is it essential to, or why is it desirable to have a probability distribution like this? It's because when we write a matrix, we are writing it in some basis. There is an implicit choice of basis in that. What you would like in your ensemble is to have this probability distribution to be independent of the basis. So the basis changes are orthogonal transformations, not to be actually confused with this orthogonal transformation. Any orthogonal transformation, let's say some random, any orthogonal transformation, we require that the distribution of the matrix elements under such an orthogonal transformation gives you some other matrix M prime. It will be still symmetric, X prime, Z prime, Z prime, Y prime. We require that these also be distributed in the same way as X, Y, and Z was. And that is assured because of this trace M square is an invariant under orthogonal transformations. So if you were to make this transformation M prime into this, and it's orthogonal, meaning that's the meaning of orthogonal, then we can see that the probability of finding, so this is the probability density of finding M. M is just X, Y, Z. You can just think of it as a joint probability distribution of matrix elements. And then the measure of X, Y, and Z, there are only 3 of them. And so that's the volume in this X, Y, Z space. So that should remain invariant under this construct. So that means that actually this is like P prime, usually, M prime, dx prime, dy prime, dz prime. And it's an invariant ensemble if it is true that this P prime is also not there. It's actually the same function. So the probability distribution does not change at all. You could think about it as an equilibrium distribution under the orthogonal conjugation by orthogonal matrices. That is what your ensemble choice is. So, you can do this transformation. So this OR also has exactly the same structure with this cos theta, sin theta. So you can put that in here, find out explicitly the connection between X prime, Y prime, Z prime, and X, Y, Z. Just write it out as, oh God, doesn't work. So, yeah, so it's an invariant ensemble if this is true, and therefore this is an invariant ensemble, and you can prove that this dx prime, dx, dy, dz is actually equal to this measure is equal to this measure under orthogonal conjugation. it's actually a calculation. And in general, it's a nice calculation, or you can do it in several different ways. But I'm not going to do it. It's just a matter of calculating a Jacobian. And invariant ensembles are those which under this, under some transformation, under some group, and in this case, the relevant group is the orthogonal group, it leaves the ensemble itself invariant. So that's why it's called the Gaussian orthogonal ensemble. The orthogonal is coming from the group under which the ensemble is invariant. Okay? So, and we will come to the importance of it being Gaussian in a minute. Okay? But now let's go to our task of actually finding out this distribution of these eigenvalues and eigenangle. That is also a conjugation, but this is, you're taking a particular element, or let's say, of the random matrix ensemble, one of your computer realizations, you can diagonalize it. That defines a basis. It's a particular basis, and you can get eigenvalues from that. So you diagonalize that, and you write this. So now, in this case, let me remove this R. So that's actually the eigenvector matrix. So, but it's the same thing, except that now this this is actually the diagonal matrix here, and that's the diagonalization. Okay. Sorry. Oh yeah, thanks. I think I had, thanks. So you do that and calculate now the Jacobian, which would be a Jacobian, let's say, between, so there is x, y, z, is lambda 1, lambda 2, theta. So derivative of x with respect to lambda 1, derivative of x with respect to lambda 2, derivative of x with respect to theta, etc. And you get this 3 by 3 matrix, whose determinant is what is going to determine the Jacobian of this transformation from this matrix elements to these set of things. And remarkably enough, that determinant does not depend on theta, it just depends on these eigenvalues in a very simple way. There are only two eigenvalues, it's just lambda 1 minus lambda 2. And therefore, when we make this transformation from the matrix element space, that's the probability of finding the matrix in the neighborhood of M and M plus dm. When we make the transformation, since this factor here is just coming from, this is coming from the 1 over 2 sigma squared trace m squared. Trace m squared is just the sum of the eigenvalues squared. Nothing about the eigenvectors there. And this is the modulus of the Jacobian. So that's just modulus of these eigenvalues. Distribution, I mean the difference. And that's the measure d lambda 1, d lambda 2, d theta. Okay, so that's actually for this 2 by 2 matrix, that is the joint probability distribution in the eigenvalue eigenvector space. And there are several observations. First of all, that the eigenvector is uniformly distributed. This theta, which is determining where the eigenvector is uniformly distributed on this circle. Not really a surprise, because your ensemble is invariant under orthogonal transformations, or in this case, just rotations. So there is no preferred direction, and it's just uniformly distributed. Actually, eigenvectors are interesting for us, but traditionally it's the eigenvalues which have been studied very extensively, because actually they are much more complicated. Eigenvectors are really simple. So the eigenvector distribution, if you were to integrate out the theta or just neglect it, so that's the probability, joint probability distribution of the two eigenvalues of this 2 by 2 random matrix is simply given by this. This is a normalization factor which you can find. So, so you see already the Wigner surmise coming out that if lambda 1 is lambda 2, this vanishes. So the probability of finding the two eigenvalues very close by is very small. And also, all the correlations between the eigenvalues reside here in the Jacobian of the transformation. This is trace m squared is actually independent, normally distributed numbers. So this is the whole thing. And then now you can find the gap distribution or the spacing between these two levels is simply this. There's a 1 missing there, lambda 1 minus lambda 2. So you can do this integral, put it in there, leave it as an exercise for you to find that you get the Wigner surmise. Actually, it's already there, literally, right? The S is coming from here, the single power that's there. And these constants, pi by 2 and pi by 4, which is actually fixed by the sigma square, is fixed so that both the mean is 1, I mean that as any probability distribution should be, and the average of the mean is also 1, which is what we will get when we unfold different spectra. Because we have widely different contexts from which we are getting these eigenvalues, we put them all into one framework by doing this unfolding, and so that we can compare all of them. So once you do that, you get this thing. And so Wigner derived this for 2 by 2 matrices, and then he surmised that this is actually true for n by n matrices, which is a very absolutely bold thing to do. And for n by n, orthogonal matrices are similarly defined. They are real symmetric matrices M with diagonal elements from this normally distributed distribution of diagonal elements with half of the variance. So that the probability density of the matrix M is given by simply, there's a minus sign missing there, e to the minus trace m squared. And C is a normalization. So you can generate it in many ways. So, I mean, it's actually very simple to generate because just by its construction, it's just independent random numbers. And the joint probability distribution of the eigenvalues now is a generalization of what I just wrote. And this is a factor just coming from the trace m squared. They are independent. All the correlations between these eigenvalues are in this determinant calculation of the transformation, and it actually is a van der Monde determinant, and it's a product of every pair of eigenvalues, modulus every pair of eigenvalues, which is, it's actually quite nice to see this without any calculation. If you see in this article is some arguments based on what kind of a polynomial it should be, and the fact that the Jacobian should vanish if any two of these eigenvalues are exactly equal. That itself gives you this. Finding this normalization constant is a non-trivial thing. It involves some Selbach integrals. See the book of Mehta, but it's known. Okay, so this is the joint probability distribution. But from this to find the nearest neighbor spacing distribution, as we found here, is again highly non-trivial. And it's not known in a completely closed form. But the remarkable thing is that even in this large matrix, if you were to find the spacing distribution, you will find that it's extremely close to this. So that's why this is still used, and it's such an important thing. That this 2 by 2 is sufficient calculation to do for the large. That's why we saw that this surmise was holding for all of this nuclear data ensemble or large calculations. It was still pretty good. But there are much more analytical results known about that. And this statistics, analytically, it is not really convenient to calculate. But numerically, it is. Okay. So now that we have talked a bit about these random matrices, suppose you were to take an n by n random matrix, construct it according to that prescription, what kind of eigenvalues do you expect? How large should the eigenvalues be? So you can easily see that by this argument. So trace m squared is just the sum of the eigenvalue squared, but you know that that's also the sum of the squares of the matrix elements. And now you make use of the fact that that these are normally distributed with a variance sigma square by 2 for all the off-diagonal elements, and then you can estimate that this is going as n squared. So trace m squared is going as n squared. And there are n eigenvalues, so n times, So a typical eigenvalue, n times this typical eigenvalue square is going as n squared. So a typical eigenvalue square is going as n. N is the size of the matrix. So you would expect that the eigenvalues are of the size of square root of n. If you construct a 100 by 100 random matrix and you diagonalize it, you would expect, let's say that sigma is 1, you would expect that the eigenvalues are some maximum, they're around 10, minus 10 to 10, that kind of range of eigenvalues. So in fact, if you do the distribution of the eigenvalues, that means you integrate out every other lambdas except just one, you get the density of these eigenvalues. That is the famous semicircle law of Wigner again. So the Wigner semicircle law, which is given by this. This is in the large n limit asymptotically after proper scaling. That is simply the density of these eigenvalues. So notice that we started with just one of them being a Gaussian, and then if you take smaller matrices, there will be oscillations and so on. Finally, it ends after some normalization to something which looks like a semicircle. It's called a semicircle, looks more like an ellipse. That's how. If you take a random matrix, probability of getting degenerate eigenvalues is 0. That's what it also says. If you get it, go back. I mean, if you get in any calculation, if you get a degenerate eigenvalue, it's probably some symmetry or something, and you don't expect these to be valid. Okay, so the Gaussian orthogonal ensemble is what is a set of real matrices, and we expect that this ensemble is valid, or is applicable rather, to systems which respect time reversal symmetry. So time reversal symmetry is intimately connected to the fact that your Hamiltonian operator can be written in a real basis. I mean, such that it's real. Time reversal symmetry is an anti-unitary symmetry. What it says is that, what it implies is that, I mean, if you take some Hamiltonian, some operator, you can express it in some complex spaces, it would give you a complex Hamiltonian. So why is this applicable is that even if you give any arbitrary basis that's complex, you can find, because of the existence of this time reversal symmetry operator, you can find a so-called time reversal adapted basis in which that Hamiltonian will be real. So, like, all our elementary examples, harmonic oscillator and particle in a box, they're all real eigenfunctions. Although we have this I floating around in quantum mechanics, it's because of the presence of time reversal symmetry. And so they're applicable if there's time reversal symmetry. If there's no time reversal symmetry, then the ensemble changes to that of the unitary ensemble. The role played by this orthogonal transformation is now played by a unitary transformation. There's to be conjugation under a unitary transformation. Otherwise, the trace m square means that you're taking all the real, now the elements are, elements of the random matrix are complex numbers with independent real part and imaginary part normally distributed. And that is the joint probability distribution. Again, trace m squared ensures that it's invariant under this conjugation, and that's known as the Gaussian unitary because that underlying group is unitary. And the spacing distribution from a 2x2 calculation, so Wigner surmise, similar to that, is giving you this s squared e to the minus s squared. As I said, there's more level repulsion in this case, quadratic level repulsion. And the generalization is a beautiful joint probability distribution. It's just, now there's no modulus, lambda I minus lambda j whole squared. So that's, this 2 is related to the fact that there is a 2 there. That's exactly the origin of that 2, it's quadratic level repulsion. So this is the correlation between these eigenvalues in this case. And in general, we can put a beta there, and write a joint probability distribution of GOE and GUE in this form. And beta is 2 for the case of UE, and beta is 1 for the case of the orthogonal ensemble. And actually, there is a, So we may generalize these ensembles so that it still remains an invariant ensemble by just replacing trace m squared by some trace of some function of the matrix. So, like for example, something like this. But in this case, we can write down the joint probability distribution of eigenvalues easily, but actually the ensemble itself is obscure. How to construct this ensemble, because the elements are no more independent. Like this is an interacting, you might call it an interacting model, and such matrices and ensembles have been studied in context of quantum gravity under the name matrix models. But there is this theorem, and this is what is very interesting, of Porter and Rosenzweig, which says that an invariant ensemble, like invariant under orthogonal transformations, we fix our mind, fix our thoughts on that, has independent matrix elements if and only if this V of H, this function here, is quadratic. That is, the ensemble is Gaussian. So that's the importance of a Gaussian ensemble. If you require it to be both independent and invariant matrix elements, then there's only one unique choice. That's these Gaussian ensembles. Okay? So there are generalizations where it's symmetric, and it's independent, but it's not invariant. Most of the matrices really are like that. Those are Wigner matrices, and very little is known about them except that their probability distribution is actually semicircle. So it has been shown that asymptotically, even if without invariance, the semicircle emerges as a universal law. In fact, the semicircle is the equivalent of the normal distribution for matrices, random matrices. Much like, for example, joint probability distributions are unknown for these larger class of matrices that are called Wigner matrices. And then there are circular ensembles. I'm not going to go into them, but we looked at quantum maps, which are unitary operators. So rather than Hermitian, we have to look at unitary operators and random unitary operators. They're very useful in quantum information and so forth. I'm not going to go into it, but Dyson studied this back in the probably 60s. So the circular orthogonal ensemble and circular unitary ensemble. Circular orthogonal ensemble consists of unitary matrices that are symmetric and are applicable again to time reversal symmetric systems. But the good thing, why we don't have to worry about it, is that the fluctuation properties of these ensembles are the same as that of the GOE and GUE. Namely, the Wigner surmise will still work for a COE ensemble. If you have a time reversal symmetric Floquet operator, this will still work. But it does not work for a 2 by 2. If you take a 2 by 2 random unitary matrix, this is certainly, you won't get the Wigner surmise. Okay? But nevertheless, for large n, it is true that it follows the orthogonal and unitary ensembles. Okay. So to summarize, if the system is integrable, we have a very different spacing distribution, e to the minus s. If it is chaotic and has time reversal symmetry, it has linear level repulsion and follows the Wigner surmise here with beta is 1. And if it's chaotic without time reversal symmetry, it follows beta is 2. There's one more canonical ensemble which I have not mentioned called the Gaussian symplectic ensemble, but I'm not going to talk about that. You can find it, I mean, the entries are quaternions and it's a generalization of this. So another quantity which has been used rather recently, especially in spin chains and so on, is the ratio of spacings. Rather than doing unfolding, which may be cumbersome, or if you're too lazy to do that, you just take the raw levels and you find the spacing. You find the spacings between two consecutive things, and you take the ratio of them. Because you're taking the ratio, you kind of get rid of the mean mean or density of states in this at this level. And then you ask for the distribution of these. So there is a surmise based on 3 levels. Now you need 3 levels because you need the ratio of spacings. So you need at least 3 levels to get the ratio of these spacings. So there's a similar thing. We know the joint probability distribution of n equals 3 by 3 random matrices. You can use that to derive this ratio of spacings and then surmise that this is actually valid for larger matrices. Turns out that that's still true. And you have, again, so this is what the ratio of spacings would look for Poisson. And GOE, GUE, and this is the other ensemble I said. The other ensemble, the spacing distribution, the GSE, goes as s to the power 4. So it has even more level repulsion than this. So beta is 4 in that case. Some e to the minus s squared. With some really scary numbers in these coefficients, like 2 to the power 18 or something. But anyways, so that's a neat practical way of finding if something is following a random matrix ensemble. Okay, so I'm just going to very briefly talk about eigenfunctions of random matrices. It's briefly is enough because they're really simple objects once I say what they are. Like in this case, is just uniformly distributed on this. The generalization of that is that they're just uniformly distributed on the normalization sphere, right? So now we are going to go over into the eigenvectors of these random matrices. And each of the matrix which you have gives you an eigenvector, so you have an eigenvector ensemble. And you can ask about what is the distribution of these eigenvectors. Now, to study eigenvectors, we need to go to a particular basis. So let's say that we have chosen some basis, some fixed orthonormal basis, and we look at the components xj. So this is the eigenvector which you have got from your matrix. J is some fixed basis, let's say the basis in which you have done your diagonalizations. And you get these numbers. And the joint probability distribution of these numbers is just fixed by the normalization, nothing else. There's no other information. All other directions are equivalent. In this high dimensional sphere, there is no particular direction chosen. So it's just this large sphere of dimension n-1. So it's an n-1 dimensional normalization sphere if this is a real number, as in the case of the GOE. So it's got much less correlations than the eigenvalue correlation, but nevertheless it's mildly correlated because of this delta function there. There's a normalization that you can calculate. I've done this thing. You do the exercises. It's a simple calculation. And what you can do from this is find the distribution of a single eigenvector component. What do you think it would be from your experience? A single eigenvector component. You see, when you do statistical physics, this is nothing but the microcanonical ensemble for an ideal gas, where this is the energy and these are the momentum squares, isn't it? And what is the distribution for a single component of momentum? A single particle's single component of momentum. Huh? Yeah, I can hear the answer. Maxwell-Boltzmann distribution, a normal distribution, right? So it's actually an exercise which you can do here exactly as in the microcanonical. The math is the same. You integrate out everything else except 1, and you will get this distribution. N is the n by n matrix. That's a number of components which you have. And in the limit, when n is large, show that that's a normal distribution. So each of the components is that each of the components are normally distributed simply follows from this fact that they are uniformly distributed on the sphere, sometimes called Haar distributed. And so the variance of this is simply related to the size, so 1 over the size of the matrix. So as the matrix sizes increase, they get more and more sharply P. And so if we were to rescale this, these components with the size of the matrix, the intensities, then they are simply normally distributed. Okay? So you can find out how the intensities, that's the xj squares, are distributed. It's a chi-square distribution. Okay, so if you were to look at some things, now how do we quantify these states? They will look something very random. And if you look at their distribution, it will be a Gaussian distribution. To quantify how spread out they are, you can look at some quantity like this, xj to the power of 4, you sum up over all j. It gives you what's called an inverse participation ratio. And the participation ratio itself is just the inverse of this. And that gives you roughly how many components of j, how many components are significant. So that's just, again, a simple calculation, because you know that the distribution of each of these things is this normal distribution. So to find average of x power 4 is simple. It's just this integral here. So in the large n limit, it's 3 by n is the inverse participation ratio. Or the participation ratio itself is n by 3. It says that if you take a random state of dimension n, roughly about 1/3 of the components are important, significant. The rest of it is not really significant. If all of them were significant, it would be exactly n, but that would be a very uniform state. It's actually not at all a typical or random state. So if you do the same for GUE eigenvectors, they are now complex, and they are, again, that's simply determined by the normalization sphere, and you can look at the distribution of the intensities. They are now uniform on a simplex. And you can find out the distribution of the, you can find out marginal distributions. You can find out the distribution of a single component. You will find that a single intensity component is exponentially distributed. So the question is whether if we add to this GOE or random matrix, which is Gaussian distributed, something which is non-Gaussian, some kind of noise which is non-Gaussian, whether it affects the eigenvectors. Is that the, well, yeah. So I think not. I think that it would be still very much n by 3. It's not sensitive to the fact that it's a Gaussian distribution. No. You have to do much more. You have to do something else to get localization, like cut off, make it almost banded, or do something else to get yeah. So actually, I think the Wigner ensemble eigenvectors, I don't know how much is known about them, but that would be essentially that kind of question. And I suspect that they're also to a large extent looking like these. Yeah, so you can find out the inverse participation ratio in this, and that gives you 2 by n, or that is n by 2 components that are significant. So time reversal breaking would generally delocalize slightly the state. It would go from about 1/3 to 1/2 of the Hilbert space. This also seems kind of reasonable. Okay, so here actually I have a picture. Since we talked about the standard map, you can do this exercise. We wrote down the standard map. It's there in the notes. You can diagonalize the standard map for different values of n, which is the dimension of this matrix here. Is also in Planck constant in that interpretation. So n equals 100. And then you can find out the eigenvectors. There are 100 eigenvectors. You can find out their participation ratios in position space and in momentum space. Now there are two different physically important bases. And then you can see how it is changing. You can average it over the whole spectrum and see how it is changing as a function of this chaos parameter. And what you would see is these kind of graphs. I have normalized the participation ratio divided by n. You would see that in the position basis, it's actually pretty large. So it would be kind of delocalized in the position basis, the eigenstates. They get more localized as chaos develops. And when in deep chaos region, they would become about half, which is what random matrix theory predicts. So these states are becoming random matrix theory-like in these regions where there is chaos. In the momentum representation, it starts from being localized. And actually, you can understand that just easily, semi-classically, from just the phase space, because you see the invariant structures are sort of parallel to the q-axis, almost constant momentum. It results in localization and momentum, and delocalization happens when there is chaos, and then they meet after some time. It doesn't matter what basis you choose. For random states, it should not matter what basis you choose, and that's illustrated well here. You can do this calculation, I hope. So that's an illustration of whatever we have been talking about in a dynamical system, which is not a random matrix, but nevertheless, it holds. Okay, I think I don't have a whole lot of time for this, but let me see. I want to introduce another ensemble, which is very useful in the study of entanglement. And its motivations are the following. I believe there's already been a discussion of entanglement in this session due to Peter. So I'm going to assume some background. And this is let's say a two-particle system, bipartite, okay? And we have here a eigenstate, or any state, need not be an eigenstate, in some basis ij. So these are the matrix elements aij, okay? Now you can construct states or reduced density matrices of each of these particles by partially tracing out the other. So you will get the density, the state of the first particle, state of the second particle, okay? How does this relate to matrices? You see, out of this coefficient matrix, out of this aij, we can construct a matrix, let's call that coefficient matrix, so this is just the matrix aij, we just populate it by this matrix aij. In general, it's a rectangular matrix. The dimension of H1 and H2 need not be the same. But these reduced density matrices, and you should be able to do that from just algebra of Ketz, is the following. Rho 1 is A adjoint. By construction, a positive matrix as it should be, and rho 2 is similarly A dagger A, except for some transpose. So from these matrices A, you can construct these reduced density matrices just by doing this construction A dagger. So, and you know that the eigenvalues of these reduced density matrices are very important numbers. Let's call them Schmidt eigenvalues. They are positive numbers which add to 1. They are probabilities. And they're important because the state can be re-expressed in terms of the Schmidt decomposition like this, where these are the square root of these eigenvalues. And the entanglement in this bipartite state is simply the von Neumann entropy of these reduced density matrices. In terms of those eigenvalues, it's simply this, lambda log lambda. That gives you the entanglement. So we could ask the following question. If we were to choose a state randomly, a bipartite state randomly in the Hilbert space, as we have been discussing, then what sort of distribution is there for these eigenvalues of the reduced density matrix? So then it's a problem of finding out the distribution of eigenvalues of matrices such as this, mm dagger divided by trace mm dagger, where M is a random matrix with fully Gaussian random entries. Not a Hermitian matrix, it's just this Aij unnormalized. If it's normalized, then the denominator is 1, but it's basically this A matrix which I've written here, except that I've assumed that A is already normalized. Here, if it's not normalized, we just have to divide it by this. So without this denominator, this was the matrix ensemble first studied by Wishart. And he studied the matrix elements, how they are distributed, because there's no correlations in the matrix elements due to this construction. But the JPDF of eigenvalues was found in the 60s, and for the trace constrained ensemble was found later still, and it has the following structure. So it's almost like well, it's just complicated by the fact that N1 need not be N2, the dimension of each of them, but otherwise, this has no, there is no e to the power of minus lambda squared. That's replaced just by this product of these of these things. So basically, there's no confining potential, kind of harmonic potential in these things. But there's this van der Monde determinant is exactly the same. And this beta is exactly the same. It's 1 for time reversal symmetric, 2 for time reversal breaking. And the trace constraint is just giving you this sigma lambda I equals 1. Okay, so that's the joint probability distribution. It looks gory, but very interestingly, if you ask what's the average entanglement present in all these states, we need to do an average of this over this probability distribution. This has been done exactly for the case beta equals 2. It was conjectured by Page and proved by others. And there's an exact formula which, in the large limit of large dimensionality of the spaces, gives you this log n1 minus n1 by 2n2, where n1 and n2, remember, are this dimension of the subsystems. So if n2 is very large compared to n1, this goes away and you get that the subsystem entropy is as large as possible. Log n is the maximum possible entropy. So it's also kind of, expected in the sense that if you were to think of this other space as an environment, the subsystem, small subsystem entropy is maximized. But if they are of equal dimension, you get a minus 1/2. You can also go ahead and ask what is the distribution of each of these eigenvalues lambda I, not the joint probability distribution, but just the density of these eigenvalues. So if you normalize them by multiplying by the dimension n1, they follow a distribution which is known as the Marchenko-Pastur distribution. And it depends on the ratio of the dimensionalities. There's this parameter q, which is the ratio of these dimensionalities. If they are equal, it's equal to 1. And for example, if they are equal dimensions, that's the Marchenko-Pastur distribution. So this is again it's a universal distribution like the Wigner distribution, and it appears in all correlation matrices. It need not be Gaussian distributed. It's actually a pretty universal law, which comes from this the Marchenko-Pastur distribution. For example, I've plotted this here for different values of the ratio of the spacing, the ratio of the dimensions of the spaces. So Q equals 1, equal dimensions. You see this distribution, and otherwise it tends to become concentrated at 1, which tells you that all the eigenvalues are essentially becoming 1 over n. So it's tending towards the microcanonical ensemble. Okay, so I probably have a very little time to go into the applications of what I've talked about, especially in this about eigenvectors and this, but I would like to pause rather than rush like some express to, yeah, please. Now, area law is simply saying that actually this would be called a volume law, yeah, because let's just examine that a little bit. So yes, n is the dimensionality of the system. Suppose we have actually a many particle system, and we have split that into 2 parts. Okay, and let's say that there is L particles here, and let's say that there are qubits to fix our ideas. Then the dimensionality of this subspace is 2 power L. And the Page formula gives you logarithm of 2 power L minus some constant as your entropy. So that's going as linear, L log 2. So that's a volume law. An area law, you might say, is constant or at most log L. Random states cannot follow area law. Area laws are very special states, ground states or other kinds. Anything else? Yeah, please. No, well, that it is this, it's not this. There is some formula in terms of Hermite polynomials and so on. It's an infinite series. refer Mehta. But what was your question? If Mehta did it, that's the kind of logic that goes. No, actually, random theory is a very active area of research because of its applications from wireless communication, blah, blah, blah. There are many new books. I would suggest a book by Forrester. It's called Log Gases and something. And there are also books written by electrical engineers and mathematicians. I think Forrester is a mathematician. So it's a very active field. I don't want to give the impression that it was over in the 1960s. The Wigner law, the universality of the Wigner matrices was, I think, in part due to Terence Tao. He also has a blog on these things, so you could look at some of that. Okay, so I really have very little time. But if there are some more questions, are there? Okay, so let's just see how I go through this. It is somewhat more recent things about entanglement within many body systems that is being very actively studied. Many body quantum states drive subsystems to thermalization through although the full state remains pure and zero entropy. So this is the old mystery, but now people are looking at it more closely in terms of integrability, using some ideas of quantum information, random matrix theory, and so on. So closed many-body systems, as we know, can be integrable or not, and it's believed that non-integrable systems, with very few conserved things, they rapidly thermalize. And one of the mechanisms which is put forward is the so-called eigenstate thermalization hypothesis. So I just want to give, since we talked about quantum chaos in some simple systems, I want to just show you how some of those simple systems can be used to study some of these questions. Especially, let's just take two chaotic systems, couple them together. We know that a standard map is chaotic. We've been talking about it. We also saw how to quantize it. Let's couple them together. Okay, so this has been studied also by many people with other motivations. But we can quantize this easily. Now it's a bipartite space, so there's a U1 tensor U2 for these individual maps and an interaction. But unlike a Hamiltonian, it's a unitary operator. It's quantum maps, they are unitary operator. We can ask for the entanglement properties of the eigenstates of this unitary operator or this flow K operator. What will happen? Does chaos aid entanglement or the opposite? So this was some early work of ours about this. So we take two standard maps. Each one of them is K is small, 0.1, 0.15, and diagonalize it with different values of n. So if n is 15, we have n squared dimensions. So we take all the eigen functions, find out the entanglement entropy, simply as described here, find out the reduced density matrices and their entropies, average it, and plot it as a function of coupling. You will see that as coupling increases, when coupling is 0, however large your things are, your K1, K2 is, entanglement is 0. And then it progressively increases, and then it saturates on some value which depends on your dimensionality. As the dimensionality is increased, this value of entanglement to which it saturates increases. And this saturation value is exactly what is described by random matrix theory, which I said from the Marchenko-Pastur law and the Page formula. In this case, they are equal dimensionality, so it's log n minus 1/2. So that's the average entropy to which it goes to. So you can see that. And so what it seems to imply is that chaos basically produces states that are random. It's not surprising. And the fact that random states have large entanglement, nearly the maximum possible entanglement, implies that chaos is going to be good as far as entanglement is concerned, is going to create entanglement. So this is what happens, not average, but just across one particular spectrum. So there are 1,600 eigenstates here, and we calculate the entanglement in each one of them and plot it here. And you see that most of the eigenstates are clustering around this line, which is of the random matrix theory. Log n minus half, most of them are here, and there are deviations. In fact, I should say that random matrix theory is only so much interesting as it talks about deviations, because it's a universality. You don't want everybody to look the same. Deviations are very important and interesting, and they have information about them. So these deviations, these states are very interesting. They're kind of localized states. We can go back and study them. But if we increase this interaction even more, they will all disappear and they will all become random matrix-like large entanglement. Okay? And this is what happens with time for a similar system. Two coupled large tops. You start with an unentangled state. Now this is time. And you see that entanglement is produced and it reaches this random matrix value asymptotically. Actually, you can't see very clearly, but if you start from a maximally entangled state, which is here, it disentangles till it becomes like the rest of the world. And so that's what happens in this. So quantum chaotic time evolution leads to near maximum entanglement. And we talked about this Marchenko-Pastur distribution that can also be found in such systems. You can look at time evolving states or eigenstates, look at subsystems and look at how they're so-called, it's one of the jargon is entanglement spectrum. These eigenvalues are sometimes referred to as an entanglement spectrum, how they are distributed, and they fit reasonably well the Marchenko-Pastur distributions. So this is also true for many body systems. Here we have a spin chain, an Ising spin chain with a transverse field and a longitudinal field, possible to change theta. So theta equal to 0 gives us a longitudinal field alone, trivially integrable. Theta is 90 degrees. You've got a transverse field, which is a very interesting, but still integrable model that has been studied for a long time. But for intermediate thetas between 0 and pi by 2, it's actually non-integrable. You have to symmetry reduce. Here there is a clear symmetry. It's a clean model. There is a symmetry of, even if you have open boundary conditions, there's a symmetry of reflection or parity. So you have to reduce symmetry, important step, before you do any analysis. So let's look at the energy levels as a function of the angle of tilt. By the way, this work is with Karthik, who is now, I'm not sure where. I think he is, well, yeah, he's doing some experiments in Europe. Aditya Sharma is somewhere in this room, I think, there. He's now a faculty in IISER Bhopal. So energy as a function of the angle of tilt. So this is angle of tilt is 0. This is Ising. There's huge amount of degeneracy. And they're all lifted by just changing this angle. This is another integrable point. So the non-integrable lies somewhere here. And you can see, like I showed you yesterday, various different energy plots. They are looking like that. There's a spaghetti here with avoided crossings. And that's a clear signature of non-integrability. You could also look at spacing ratios, and you find that, that it will be going from something which is like a Poisson to a Wigner surmise. It's probably not that great data. I don't know. Maybe we had only 10 spins with some symmetry reduction. So it's probably not a very large dimensional thing. The interesting thing is actually the fact that it's a Gaussian here, a Wigner distribution here. You might think that maybe it's at an intermediate angle of pi by 4 or something, because pi by 2 is integrable and 0 is integrable. Actually, it turns out that it's most non-integrable, very close to the integrable case of pi by 2, the transverse Ising model. You can see here the entanglement entropy plotted as a function of this angle of tilt. This one here, it's increasing across the tilt. This is the pi by 2. You can see that the entropy is coming down, but it's largest somewhere in its vicinity. And then it's all coming down. This is some other kinds of entanglement. I'm not going to talk about that. Once we go to many body systems, there is many entanglements, because you can talk about entanglement of one part with another subpart and so on. It's a more complicated thing, but usually people just talk about one block with its complement, and usually one half of the block, as has been done here. But there are very interesting questions out of that. And Another a place where you can see this is another kind of spin chains that people have studied more recently. This is next to nearest neighbor transverse field, but there's a disorder put in this interaction here. And in these kind of disordered models, you find a transition to localization. But in the cases where it is ergodic, these dotted lines are exactly the page formula. So this is supposed to be an ergodic phase or random matrix kind of delocalized phase in the many-body system, and which all gets localized here in this many-body localization. A lot of experiments, interesting experiments that are going on now with where people are trying to look at few-body systems and keep the state pure for a longer period of time, measure some of these, they measure the state itself or some observable, and see what happens and if they're non-integrable versus integrable. So this is a more recent 2016 experiment from Griner's group where they study a so-called a Bose-Hubbard model, realization of a Bose-Hubbard model. And well, there, I don't know what are the critical lines to read here. We experimentally studied the emergence of statistical mechanics in a quantum state and observed the fundamental role of quantum entanglement in facilitating this emergence. Microscopy of an evolving quantum state indicates that a full quantum state remains pure, whereas thermalization occurs on a local scale. We directly measured entanglement entropy, which assumes the role of thermal entropy in thermalization. Entanglement creates local entropy that validates the use of statistical mechanics, and they say that, therefore, it supports the eigenstate thermalization hypotheses. Another experiment, which is sort of related to what we have been discussing, concerns this kick top. So this is like, we didn't actually put this particular model, but we kicked so many things. So this is kicking a large spin. Jy is just a rotation, Jz squared. So this is another very popular model because it's finite dimensional. And as the strength of this kicking is increased, it goes into chaos. This particular experiment realized this using 3 qubits. So basically, you can consider these 3 qubits as constructing a larger spin, or spin 3/2. And so you can write this also as an Ising model if you wish. I just write that out more clearly here. So if you construct this kind of a collective operator, then you could think of this as a subspace of a transverse kicked transverse Ising model in which there's an all-to-all interaction. And the thermodynamic limit is simply the number of spins going to infinity, which is actually the classical limit, in which case the map shows a transition to chaos like what we have been seeing. Now it's a map on the sphere, on the angular momentum sphere to itself, but it's still a 2-dimensional area-preserving mapping. And you see this as this parameter of this torsion, or K, is changed, it goes from an integrable to mixed to fully integrable system. I think I haven't written the values here, but this is, I think, 1, 3, and 6. So in the experiment, what they do is they just take these 3 qubits, they say that they have engineered this is a superconducting qubit experiment, and they start with a pure state of 1 qubit. So they're doing tomography of 1 qubit and seeing what that state is on the Bloch sphere. So it starts from a pure state, and it loses purity, it's going into the Bloch sphere, and its entropy is increasing. So this is a full state tomography over 20 time kicks, 20 kicks of this. And then they do an average over this time. And they observe, so they can start their initial states from anywhere in the phase space, a coherent state anywhere in the phase space, do the experiment over 20 time steps, and then average over this, and then they plot this average in phase space. And this is for the case when it's not very chaotic. Kappa is 0.5. This is in the case when kappa is 2.5, intermediate. They can't go for very large kappa as experimental limitation. So quite remarkably, it's a very small system. H is very large. It's a very quantum system. But you can still see some kind of correspondence between this and classical dynamics. So that means that what's plotted here is the entropy of that single qubit. the entropy of that single qubit is large if it is somewhat in a delocalized phase. And if it's in the localized regions, it's small. And that's more clear in this case where there is chaos here and there's regular regions here. This entanglement is large if you start out from a chaotic part of the phase space. And it's smaller if you start out from a regular part of phase space. I mean, it's, at this point, it's more or less artist's impression maybe, but it's not, but it's quite impressive that a 3-qubit case shows you some of these things. There are some details. We have also worked with the data, but I don't have time to go into that. There are some interesting data. But, okay, so this is another thing from their picture. This is this paper from Martinez group. And what is plotted here is overlap of an average of the density, the reduced density, average, time average, with the microcanonical average. So in this case, the microcanonical average, so you have a single qubit. The density matrix microcanonical average is just the most mixed state. Both these states are equally populated. That's it. So they are seeing the distance between that and the time average state. And what they find is that if the initial state was here, middle of the island, and is regular, it's still quite, okay, it's an overlap. So if the overlap is 1, it's perfect. That's ergodic. So it's a small overlap if you start from here. And if you start from here or here, they are actually much larger and closer to the ergodic. That's the best you can really do with a 3-qubit system, and given the limitations of the experiment. Yeah, I just want to say that actually it's a peculiar thing that they started with 2 initial conditions, which are really the same, in the sense that if you start from here and iterate once, you go there. It's actually part of a period 4, so 1 here, 1 there. But experimentally, they have the data for that. Yeah.
They keep making measurements, right? So, yeah. I mean, doesn't that, it's then different dynamics, right?
So I guess it's all an ensemble thing. So they have to do a full state tomography. It's an ensemble measurement.
It's like you keep.
No, the dynamics is still unitary, but what you're doing is your ensemble is starting from a huge collection of from a collection of states, which are collection of systems which are starting from the same state. You need to be able to initialize your state pretty well.
In time, you measure a separate set at...
yeah, you have to measure a different set at a different time. Yeah. Somehow the measurement problem is never a problem for those who are doing experiments. Okay, so I think I should stop, but these things kind of imply something which is the eigenstate thermalization hypothesis. I have 2 slides on it. Abhishek, should I really 2 more minutes on this? But I have 3 slides, of which most of it is pictures. So maybe I can go through this. So let's clear our minds, set it to 0, and start from an initial state psi of 0, evolve it in time according to this Hamiltonian. We get the state psi of t. We can expand this in the eigenstates of H and elementary quantum mechanics. We can write it in terms of superpositions of these eigenstates, where the C alpha are the overlap of the initial state with the energy eigenstates. Okay? So far, so good. And then we can take the density matrix, not the reduced density matrix, this density matrix of the state, and then write it like this. And in the absence of any degeneracies, we can do an average over time. So this is our ergodicity. What we are trying to do is see, we had this picture, in fact, I think, next slide, there is this thing. We had this picture where we discussed that if you start from an initial state, like we did in the cat map, and then after some time, chaos pushes it into, it goes ergodically, and in fact, there's also mixing on this energy shell. After some time, it goes almost uniformly covers it or whatever, and that's the thermal state, microcanonical ensemble. But what happens in the quantum case? So if you were to do a time average of the state, all of these vanish in the long time limit if there's no degeneracy, and it only picks the state when alpha equals beta. and you get modulus of C alpha square and this. So this is sometimes referred to in this literature as a diagonal ensemble. So a diagonal ensemble is diagonal because it's only diagonal in the energy eigenbasis, like the canonical ensemble. But unlike the canonical ensemble, it's dependent on the initial state, the C alpha square. C alpha square is overlap of the eigenstates with your initial state. So initial state is very much there after averaging over time, initial state information. Okay, so if you take an observable A and do a time average, then that is nothing but the expectation value of that operator with this diagonal ensemble, easy to see. Okay, so that's the use of this diagonal ensemble with this observable. But the question mark is whether that's equal to a microcanonical average. What is a microcanonical average? The average of the expectation value, so the average of the expectation value of this operator over a bunch of eigenstates over some energy range delta E. That is a microcanonical ensemble where this E itself is the average energy of this observable. The observable will have some average energy about which you're expecting that that this will be true. So this is a microcanonical ensemble, but this was completely independent of the initial state. There is no information about that. So the question is whether this long time limit is the microcanonical. So this is the problem of thermalization. And the eigenstate thermalization hypothesis says that this is true if the system is sufficiently non-integrable, ergodic, sufficiently non-integrable, chaotic, and follows some kind of random matrix-like eigenstates. And the basic argument is that the expectation value of an observable is in some energy eigenstate is in fact the microcanonical average at that energy plus fluctuations which are small. Average fluctuations are small, and average is 0 and fluctuations are exponentially small in the number of particles. So this is the hypothesis. And there are numerical evidence and some amount of evidence from individual systems, but basically it relies on this fact that the eigenstates are actually fairly complex. So if you look at this picture here, and this is from Rigol 2008's famous paper in Nature, where he put together the thermalization hypothesis initially due to Schrednicki, who also developed and worked with Deutsch, work of Deutsch earlier. So this is a picture in the quantum case where you have different energy eigenstates which are themselves pretty delocalized, just as our random states were. Large participation ratios and so on, highly delocalized, even to begin with. But the initial state is not thermal. And that's because there's some particular superposition of this which is making it very special. And that is, all these phases are there. So there is actually coherence in this initial state. But each of the states is themselves thermal. And with time, there's a dephasing going on, and this coherence is lost, and it becomes like a thermal state. So that's the picture which, roughly, that's the picture which is there in this context. So I'll just show this numerical evidence from a model which is a Bose-Hubbard model, a hardcore boson model of 6 particles on 17 lattice sites from this recent review. It's a readable, nice review by Deutsch. And there is this numerical calculation of this operator N1, N2. What is N1, N2? I haven't written the model, but it's the density of bosons at 2 sites, N1 and N2. Okay, so density of bosons at 2 sites, N1 and N2. You find the expectation value of that in these energy eigenstates, and you plot that as a function of energy. If the parameters are such that the Hamiltonian is non-integrable, it is this red thing which shows a kind of a smooth variation, whereas if it's integrable, it's got all over the place, and it's not a smooth variation. So the Eigenstate thermalization hypothesis in its simplest form, and I think there are different forms, is saying that if you take some many-body non-integrable system and you take an operator, and it's not very clear what is the nature of that operator, but typically, again, it's considered to be a local operator in some many-body space, and you look at it as a function of this energy eigenstate's expectation value, it does not change much if you change the energy eigenstate to the neighboring one. Qualitatively, this is small. Let's say that this is smaller than something which is exponential in the number of particles, or it's going as something which is exponential in the number of particles. So that means that if you go back to the sum in this expectation values here, although you are going to take this expectation value over many states, it's sufficient for you to construct this out of just one state, because there's hardly any variation across the microcanonical ensemble. So you don't have to do an average for over many states, but just one eigenstate. One eigenstate itself is thermal in that sense. So that's the eigenstate thermalization hypothesis. I will stop here, and thank you all for your attention over 5 days.
Questions?
Like you said that the chaotic systems give rise to these random entangled. I mean, basically give rise to entanglement, right? So
entanglement is there also if there's no chaos.
It's there, but basically it sort of increases the amount of entanglement in the system if you start from a pure state,
yeah,
or product state.
Yeah.
So what I was thinking was, isn't it natural? Because if you write down just the coefficients and you say that the coefficients are just randomly given the values.
Yeah.
So I mean, the set that you get out of the states that can be product states and the states that can be entangled states. That set is, of course, it's naturally bigger, right?
Yeah. Unentangled states are a set of measure 0.
Yeah.
Yeah. Yeah, but this is more than saying that. I mean, it's saying that it's actually nearly maximum. It's very large. It's not just saying that it's entangled. In the set of pure states, unentangled states are a set of measure 0. But this is saying that it's actually driving you to near maximum entanglement. But it's also a good question whether it is actually close to maximally entangled states. But that's another story. But it's just as far as entanglement entropy is concerned, it's nearly maximum.
Okay.
It's a somewhat non-trivial thing. But still, it's not something which is unexpected if you think about it, because chaos is going to drive it to random states.
Yeah, because that's what I was thinking, that it seemed to be really natural to, I mean...
Yes, it's not unnatural at all. I'm not claiming that.
Break for tea, and so let's thank again Arul for a really fantastic set of lectures.
Thank you.